Good evening, everyone. I'm Rishik, and I welcome you all to the last talk of the fourth day of the Limit Online Camp 2024. On behalf of the entire Limit team, I welcome Professor Joel Spencer. He received his doctorate from the Harvard University under the supervision of Andrew Gleason. Currently, he is a professor at Courant Institute of Mathematical Sciences of New York University. He's a recipient of several awards and fellowships. Notably, he became a Fellow of the American Mathematical Society in 2012 and was elected as a Fellow of the Society of the Industrial and Applied Mathematics in 2017. In 2021, he received the Leroy P. Steele Prize with Professor Noga Allen for their book, The Probabilistic Method. He works in theoretical computer science and discrete mathematics. So with great honor, I invite our speaker, Professor Joel Spencer, to present his talk on asymptopia.
Well, thank you very much. It's really a pleasure to be with all this young talent. So that's really, really great. And my talk will be something a little different. I call it asymptopia. I made up the portmanteau myself, because I think that looking at things asymptotically is really a different kind of world. And it takes some getting used to, but it's very, very powerful idea. Let me introduce you to the people because I know you have to go. So let me introduce you all to Professor Mumanti Potter. She was, like you are all, a top high school math student. And then she went to ISI Kolkata, where she got a wonderful education. And then she came to New York University, and she was my student and did a marvelous PhD dissertation. And then, and today, if she's not in Moscow or Mumbai or Melbourne, she's a professor at IISER Pune. So, Professor Potter, perhaps you can say hello to these students.
Yeah. I was. Let's hope that, okay, I'm visible now, I'm hoping. Hello, everyone. I'm still an assistant professor, so like very young, long way to go. I'm in IISER Pune, or if you want the full form, the Indian Institute of Science, Education and Research, Pune. And I have had the best possible doctoral advisor ever. So thank you so much for being my mentor, Professor Spencer. So, and and you all are going to learn so much from this talk of his and every other talk of his that you plan to attend in the near future, as well as from the book that was mentioned in his introduction. That book is like, for me, so I would say, that's the kind of book that really helped me learn the subjects leading up to my PhD. So that book is still it's something that I hold on to and cherish very dearly. So and thank you, Professor Spencer, for being you. And I'm so glad you introduced me to your audience today.
My pleasure. Okay, so next slide. So here's something from my mentor, the legendary figure, Paul Erdős. He really didn't have a home. He just traveled around and did mathematics all over the world. And he did this from maybe just after World War II till the end of his life. He would come to my house and stay for 3 days, and we would work on mathematics, and then I would spend 6 months trying to write up what we got. And he was just an amazing person. I often think of him like Ramanujan, somebody whose spirit of mathematics was just so strong. And now he's a legend, but for me, he was a very real person, and was, is, and forever will be the center of my mathematical life. Next slide. Okay, here we go. All right, so here's a theorem that you all know, but I'm going to give a different proof from an asymptotic point of view. So let's show the proof and then I'll talk it through. Next slide. Okay, so again, like most proofs, it's reductio ad absurdum. Oh, I wrote reduction ad absurdum. It's actually Latin, reductio ad absurdum. So you assume there are a finite number of primes, and then you have an encoding. Any number can be written as the product of pi to the alpha I. Let's assume r primes. And so you can encode the number n by this vector of the exponents. Okay, now, so that's fine. But now, if you look at the numbers from 1 to n, and then we're going to, in the end, think of n as being really large, what happens is the code values are only logarithmic in size because pi to the ai has to be less than or equal to n. So ai can be at most logarithmic. So that means that the total number of vectors is what's called polylog. That is a fixed power, in this case, the rth power of logarithm. So there are only polylog possible code values, but they're n values. And the thing is that when n is large, the log function is the snail function. It just grows incredibly slowly. So any power of n, of log n, grows slower than n. And therefore, we get a contradiction because we have n code values, but on the other hand, we only have polylog n code values, and that gives a contradiction. So, I mean, I know you've seen other arguments. I'm not saying this is the best argument, but this is the argument from an asymptotic point of view. Next slide. This is my colleague, who Professor Potter knows very well, Raghuvaradhan, one of the esteemed graduates of ISI Kolkata, who then came to my own institute, the Courant Institute, and has been just an absolute giant in probability theory. And this is a nice quote from him. Wonderful, wonderful man, Raghu. Okay, let's go to the next slide. Just a couple of basic facts. We want to have a notation. Let's let V sub p of a number, we're going to be looking at the number of factors. So 2025 has 2 factors of 5. So just a definition. I think most of you by now know about E, but I just, in case you don't, E is as important. In fact, you know you've reached a certain mathematical maturity when you think of E as even more important than pi, though pi is important. And here is the most beautiful asymptotic formula in my mind, is Stirling's formula for n factorial. And it's remarkably accurate. Even for n equals 10, it's within 1% of 120 when you do the calculation. And to me, it's just so beautiful. I mean, what do E and pi have to do with n factorial? And it's just one of those beauties of mathematics. And we're going to define pi of n as the number of primes less than or equal to 10. That's just a definition. And we're going to talk about the prime number theorem, that the number of primes up to n is asymptotic to n over log n. So how many primes up to a googol? Well, log of a googol is 230, so it's a googol over 230. So that's a lot of primes. That's a lot of. The idea of the primes is they get rarer, but they get rarer very, very slowly. Very, very slowly. They get rarer logarithmically slowly. Okay. All right, let's go to Conway's. John Conway was a wonderful mathematician. You may have heard of the Game of Life, and also he just had a wonderful, wonderful spirit. He passed away during COVID. He was one of the COVID casualties, but he had a great, great life. He was at Cambridge, and then he came to Princeton and did great group theory, but he loved games. He loved games. And I think for all of us, even if it's not our research, this love of games is very common in the mathematical community. Okay, let's go on to the next slide. And I want to talk about a divergent sum. That means that you add them all up, it goes to infinity. I mean, some sums like summation 2 to the minus k converge to 1. Other sums go off to infinity. And the theorem is that if you sum the reciprocals of the primes, that it goes to infinity. And again, it's reductio ad absurdum. I'll just say it quickly, but you can check the slides later if you want. Again, assume that the sum is a constant c, and then we're going to split into small primes and large primes. And we make the small primes such that the sum gets you within a half of c, so that all the large primes would only be giving a half. And now we do something similar to the previous argument. We look at small numbers, which only have the small primes. They're only polylog of those, so that's small. On the other hand, if a number is not small, it's divisible by one of the large primes. But how many numbers up to n are divisible by p? Well, less than or equal to 1 over p of them. I mean, it's actually floor of n over p, but so that's at most n over p. So the number of numbers up to n which are divisible by p is 1 over p. Even if those were disjoint sets, which they're not, the total number you'd get would be summation of n over p sub I. But we're assuming now these are the large primes, that they only add up to less than a half. So we get at most n over 2 of these large numbers, and we get at most polylog of the small numbers, and that does it, because polylog plus n over 2 can't be n. The actual result is that the sum of the reciprocals of the primes up to n does go to infinity, but amazingly small. It grows like log n. By the way, let me throw in a joke. The joke was, what does a Hungarian parrot say? And the answer is log, 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 log. Well, Hungarian mathematicians really like this asymptotic stuff. So log is incredibly slow. I mean, log, take a Google, log of a Google is 230, and log of 230 is like 5 or 6. But even more impressive, go from a 10 to the 100 to 10 to the 200. What's the difference in the log? Well, you've got an extra factor of 2 in the log, so you get an extra additive factor of log 2, 0.69 in the log. So what it says is that the sum of the reciprocals of the primes from 10 to the 100th all the way up to 10 to the 200th is only like 0.69. So it does diverge, but remarkably slowly. Okay, let's go to the next one. And here's one of the giants of computer science. It's interesting, I'm old enough to remember when theoretical computer science really didn't exist. And people would look at programs and they'd say, well, I had a program to do this in 3 hours and 11 minutes. And the other person would say, my program only took 1 hour and 46 minutes, but I had a faster and so it went like that. But Don Knuth was one of the key people that put theoretical computer science on a solid foundation. And that's the field that we have today. And also he has just this wonderful, wonderful spirit. I would just modify what he's saying there and say not only computer scientists, but mathematicians as well. And let me point out, I'm joint math and computer science. I think the combination of the two is really wonderful. Okay, let me turn Now to the next slide. And okay, so some theorems are important theorems. Some theorems are deep theorems, but this one is a fun theorem, or I call it a weird theorem. We want to look at a binomial coefficient, n factorial over a factorial b factorial, and ask how many factors of p are there in it. So in general, so I'm taking the example here. I'm taking n equals 100, a is 44, b is 56, sorry, p equals 3. So how many factors of 3 are there in 100 factorial divided by 44 factorial, 56 factorial? And here is the result. I mean, I just think this is funny. What you do is you add 44 plus 56 to get 100, but you do it in base 3. You do it in base 3. So, and when you do it in base 3, you count the number of carries when you do the addition. And that number of carries, that's the number of factors of P. So I won't give a proof, but let me give an example. Next slide. All right, so first of all, we have to please reach in back of your head and go to that central control panel, and you see it says decimal and hexadecimal and binary. There's also a spot there for ternary. Please switch that on, okay? So we're going to start thinking in terms of ternary. I'm going to just call on a volunteer. Samyak Kar, are you there? Take off your video and take off your microphone. If you're there, just say hello. Maybe not. Let me just pick. He's not able to. No problem. Let me get to. I'll pick someone else. How about Kumar? Kumar Sharat. Can you turn on your microphone and say hello? I think you're on. If you can, is your voice on? Okay, I'm having a little trouble hearing people. Okay. All right, no problem. No problem. All right, so let's switch to base 3. So base 3 is just like base 10, except you have 3 fingers instead of 10. So we're looking at, instead of v sub 3 of 100 factorial, we're looking at v sub 10 of 10,201 factorial. Okay. And what is that? How do you find the number of factors of 10? Remember, 10 is now a prime. Well, it's the multiples of 10. All right, that's 1,020. You just cut off the last digit, plus the number of multiples of 100, because those have to be double counted. So you add on another 102, plus the number of multiples of 1,000, because those have to be triple counted. So that's another 10, plus the number of multiples of 10,000. That's the, and there's one of those, and then it stops. And then similarly, 1122 factorial is 112 plus 11 plus 1. So you just keep cutting it off on the right, and then adding those up. And similarly, you get 200 plus 20 plus 2. Now, what we want, because it's n factorial over 44 factorial, 56 factorial, the number of factors of 3 is the first one minus the other 2. Okay. Now, the thing is, you might think it's 0 because, after all, 1,201 equals 1122 plus 2,002. But it's not 0. So when you look at, say, 102, you see that 102 is not 11 plus 20, because when you do the full addition, it's going to come out to 10,201. But 102 is 11 plus 20 plus the carry, So when you add these two base 3, you get 2 plus 2 is 11, carry a 1, 1 plus 2 is 10, carry a 1, 1 plus 1 is 2, 1 plus 2 is 10, carry a 1, 1. Okay, so when you get the carry, and the carry can only be 1 or 0, then what happens is the 102 minus 11 minus 20 is the carry, which is 1. And when you just add up a bunch of ones, there's a fancy word for that. It's called counting. And so you get this incredible theorem. It's really great fun. Great fun for math contests. Like you could ask a question like, how many of the binomial coefficients 20, 25 choose I do not have a factor of 3. And then you write things in base 3, and there are a lot of cute problems that you can get out of this one. So I love this theorem. It's just a lot of fun. But now let's see an application of it. We go to the next slide. If we look at the number of carries, what happens is, so like with the 10,201, there are at most 4 carries. So if you look at 10 to the 4, you'd get 10,000. I'm still working in base 3. So it's at most the 10,201. So what happens is you get an interesting thing. When you look at a binomial coefficient, you look at the prime factorization, and all of the prime powers are at most n. So that's really quite a surprising result. So what happens then is you immediately get a very nice bound. Let's look at the middle binomial coefficient, and each prime power is at most n, and the number of prime powers is pi of n by definition. So you get this inequality. The middle binomial coefficient is at most n to the pi of n, and that gives a lower bound on pi of n. Just take the log base 2 of both sides, but the log base 2 of n choose n over 2 is asymptotic to n. So you immediately get this lower bound. You don't get the n over log n, natural log of n. You get n over log base 2 of n. In fact, the natural log took 100 years to solve. So we get this lower bound, n over log base 2 of n, but it's pretty close to the real answer. Let's go to the next slide.
So I had a question.
Bound. Yeah, question, sure.
So in the previous slide, what if the n is odd?
Yes,
And
that's a
also,
very
like-
good question. In this talk, n is even. In fact, more than that, in this talk, n is a power of 2. So you're right. When you write out the talk, it turns out it's close enough. You still use the middle binomial coefficient, but you're right. It takes more work. So I'm not going to answer your question except to say it's a good question, and so this is my favorite method of proof. It's called proof by intimidation. I'm just saying, yes, it'll work for n odd. And in fact, the next thing is going to work for n as a power of 2, but I leave it to you to try to modify it for other n. It is doable, I'll say that. So the other one, the upper bound, is to notice that if p is a prime bigger than n over 2 and less than or equal to n, then p appears in the numerator of the middle binomial coefficient, but does not appear in the denominator. So you get p to the first power. It's actually a simple example of the carrying, but in this case, you just see it immediately. And so what happens is all the primes between n over 2 and n appear in the prime factorization. Now, all those primes are at least n over 2. This is something about asymptotics. I mean, they're between n over 2 and n. A posteriori, it's okay to call them greater than or equal to n over 2. It's not clear a priori, but I've done this before, so I know it'll be okay. So it's at least n over 2 times that number of primes. And so the upper bound is 2 to the n. Again, we could do better, but it wouldn't have an asymptotic effect. We take the log to the base 2, and what we get is a lower bound on the number of primes between n and 2 over n. So in particular, I'm going to just take n to be a power of 2 because that makes things easier, but you're quite right. I mean, you really need to do it for all n, but I'm going to just do it for n as a power of 2. So the number of primes between 2 to the t and 2 to the t minus 1 is at least 2 to the t over t minus 1. And now we can telescope, and we get a sum, So let's go to the next slide. So here's the example. We get, for 2 to the 100th, we get the sum we get 2 to the 100 over 99 plus the number of primes up to 2 to the 99, and that's 2 to the 99 over 98 plus the number up to 2 to the 98. So we get this sum, as you can all see it. Now, we could find a lower bound by dividing everything by 100 instead of the smaller denominators, and that gives basically twice 2 to the 100 over 100. Notice that's twice what we would have gotten for the lower bound. But really we need an upper bound, and here's something interesting about asymptotics. I mean, you've got this sum. I'm doing it for 100, but you want to do it for general t. And you've got this sum, and you know, there are a lot of beautiful formulas for sums, but this one doesn't have a beautiful formula. It just doesn't. I mean, I've looked and looked and looked, and it just doesn't. Still, you want to know asymptotically what is the sum, what is an upper bound on the sum. And it's a little tricky because the numerators are getting smaller, but the denominators are getting smaller too. So it's not at all clear a priori what's going on. But let's take the next slide and we'll see what's going on. Okay, so here's the idea. Let's go down to, let's say, 2 to the 81. Okay, now going all the way down to 2 to the 81, the denominator has gone down, but it's only gone down to 80. So instead of dividing by 100, we're dividing by 80, which is pretty close. And now what about the rest of them? Well, all the rest of them, imagine we divided by 1. Now that's a crazy thing to do because it's way, way off. But because it's small, even getting a gross upper bound on a small thing, it's still going to be small. So the small stuff, it's really 2 to the 80 over 79 plus 2 to the 79 over 78 plus ... Let's just say it's less than or equal to 2 to the 80 plus 2 to the 79 plus ... So that's 2 to the 81. And the thing is, 2 to the 81, that's like 2 to the 1, that's like a millionth or 2 millionths of 2 to the 100. Remember, 2 to the 20 is a million when you think about these things. So what happens is you really get, instead of 1/100th, you get 1/80th, and then the remaining terms are much smaller. Okay, so let's go to the next slide. And all right, there's a formal way of doing it. I think I'll just skip that about where to make the cut to give a true epsilon delta proof, but I think everybody will be able to look at this later if they want. Okay, next slide. And here's the history. So this gives the correct answer within a factor times 0.69 on the bottom and 1.36 on the top. And that was conjectured in the late 18th century. People were very good at calculation at that time. And they made this conjecture, and it took 100 years to solve it. So we're not going to do it today. It was shown remarkably, it was shown independently after 100 years by Hadamard and de la Valle-Poussin. And their proof used complex variables. And then in 1948, Atli Selberg and Paul Erdős came up with an elementary proof, but I put that in quotes because in mathematics, elementary does not mean easy. It means that it's not using advanced techniques like functions of a complex variable. So there's a little history behind it. Okay, next slide. Oh, so I think that there was a wonderful talk by Kapoor on primality, but it's so important and so beautiful, I'll just repeat what he said. There was this beautiful algorithmic question. How do you determine whether an S-digit number is prime or not? And what you want is an algorithm that's polynomial in the number of digits, not in the number. So if you try to divide by all the numbers up to root n, that takes time root n, but that's exponential in the number of digits, so you don't want to do that. And next slide. And as Kapoor said, there's the Fermat test, which is very quick. I think it's time s cubed or so. But unfortunately, there are some false positives with the Fermat test. There are no false negatives, but there are false positives. So, we're mathematicians here. Algorithms that give the wrong answer are not really algorithms. There's a wonderful term for numbers that pass the Fermat test that my friend, Professor Carl Pomerantz at Dartmouth, came up with. He said that if you pass the Fermat test, going back to Kapoor's talk, then you are an industrial strength prime. So maybe you're not a prime, but not too many numbers are not prime. Okay, next slide. And the history is just wonderful. Agarwal, Kayal, and Saxena in Kanpur, they did find the algorithm. Their original algorithm took time s to the 12. There's still an enormous amount of work on improving it, including work by themselves. Maybe there's an s cubed algorithm because that's the Fermat test algorithm, but that we don't know. So to me, here's this about the most basic question you can ask in number theory: is a number prime? And yet it turned out this was open for like 50 years. People almost immediately when they started working with computers thought about primality testing. And it wasn't until 2002 that Agarwal, Kayal, and Saxena came up with their algorithm. And the algorithm along with a proof that it worked. I mean, if you have an algorithm with no proof that it works, that doesn't count. So this was a wonderful result. Let's go to the next slide. Here's a wonderful thing from G.H. Hardy, who had this wonderful aesthetic sense of mathematics. Okay. Let's turn, the final thing, I want to turn to a result of Hardy and Ramanujan. So next slide. So here is one of their many wonderful theorems. First, I'll say it roughly, that if you take a number from 1 to n, most of the numbers have roughly log n prime factors. Here, I won't count multiple prime factors, but you could count them and get the same result, it turns out. So that's just saying it roughly, but if you've had some analysis, we can make a precise statement in terms of epsilons, and I've given this statement here. And so let's turn to next slide. So I'm not going to give the Hardy-Ramanujan proof, but rather a proof by the great Hungarian mathematician Paul Turan. And though he didn't write it this way originally, we're going to use the methods of probability. And this was an amazing breakthrough because, I mean, primes are either prime or not. So what is probability? How can you use probability? And his result was really a breakthrough. So we want to look at the number of prime factors. It's convenient to only look at the prime factors up to root n, because there's only one other, and that won't affect the asymptotics. Okay. So now we're going to turn to probability. We pick a number from 1 to n. So we think of n being very large here. And we choose it uniformly at random. And then we have the random variable that p, for each such prime p, we have the random variable that p does divide I. And what we want, and x is the total number of prime factors less than root n for the number. And what we want is that x is near log n for most I. So it's really a concentration result, that the random variable x is most of the time is near log n. Okay. So to get a concentration result, we're going to calculate the mean and variance. All right, so let's go to the next slide. All right, so the thing is that the expected value of I sub p is the probability that p divides n. Okay, it's not exactly 1 over p, but it's very, very close to 1 over p, because it's floor of n over p over n, but it's only off by 1 over n. So the expected value is the sum, and basically the 1 over n doesn't matter very much. And so the expected value is like log n from this result about summation of p inverse. Interestingly enough, even if you don't have that deep result, you still get a concentration around whatever summation of 1 over p up to root n is. Okay. And then we want the variance. Okay. So I think some of you have had some probability. If not, sorry, we'll just do it. The variance of a sum is the sum of the variances plus the sum of the covariances. So what happens is the variance of an indicator random variable, if an indicator random variable is 1 with probability alpha, its variance is alpha times 1 minus alpha. Alpha is near 1, is near 0, so the variance is very close to the expectation. So the sum of the variances is log n. But what about the covariances? So let's just think, we pick a random number from n to a Googleplex. And we have two events, divisibility by 7 and divisibility by n. By 11, sorry, divisibility by 7 and divisibility by 11. What is their covariance? That is, if you know that the number is divisible by 7, what's the chance of it being divisible by 11? Well, the covariance is practically 0, because divisibility by both of them is divisibility by 77. And so, all right, you have this problem with taking floors, but you'll see it's a relative. So what we want to say is that the covariance is near 0, and so that those terms don't really count. So let's go to the next term. Next slide, sorry. And we have to be a little bit careful that when we take the covariance of two terms, it's the product of the expectations minus the product of the minus the expectation of the product. And because of the error, it might be off, it's less than or equal to 1 over n. Actually, it might be negative. Now, this little trick that we only looked at primes up to root n, so we have fewer than n terms. So even adding all the covariances together, where it's going to be small compared to log n. And so we get that the variance is around log n. This is really the full proof. It's really this was a remarkable result, and yet, I mean, you have to fill in the details, but this is really it. This is the proof of this remarkable result. And then the final step is something you may have heard, that if you take any random variable it's got a mean and a variance. What's the probability of being lambda standard deviations off the mean? It's at most lambda to the -2. So in particular, since the standard deviation is root log n, which is little o of log n, what happens is the chance of being any constant number of standard deviations off the mean goes to 0. So we get the concentration result. Let me just finish here with next slide. That there was actually then a beautiful result by the Russian-American Mark Katz and the Hungarian Erdős. One beautiful thing about mathematics is how international it is, that they looked at this argument and they were able to improve it. And they were able to say that not only is it concentrated around log n, but it's a Gaussian. It's a Gaussian. And actually their proof, well, it requires some more steps, but surprisingly, it's not, if you have the right probability background, it's not that complicated. It's not that complicated. Okay, let me finish by a final quote by Julia Robinson. Julia Robinson was a wonderful mathematician, died sadly too young. And again, she had this wonderful spirit of mathematics. I think she's best known that she, along with my colleague Martin Davis and the mathematician Hilary Putnam, did fundamental work on what's called Hilbert's 10th problem. So I'll just not tell you what that is, and which was then the final nail in the coffin was done by the Russian Matyas Savage, but she played a fundamental role and did lots and lots of other things too. So it's always nice to remember it. And I think I'm actually right on time. So thank you very much for listening. And I hope you find lots of beauty in mathematics. And thank you very much. Thank you very much.
Thank you, sir, for the wonderful talk. If anyone has any questions, they can feel free to ask.
Thank you. Yes, the Erdős number of 1. I do have an Erdős number of 1. I'm always thinking about going on eBay and selling an Erdős number of 2. So if any of you have rich parents and are interested, well, that's my joke. Okay. But Erdős had so many great things. And one of the things was that he just had this tremendous ability to work with other people. And he would talk to somebody, and maybe it was a high school student, maybe it was a full professor, but he would see what kind of problems the person was interested in and what level they were at. And he would ask problems. He was always filled with open problems. And he would ask, and it happened to me personally. So it was just really, when you talked with him, you were drawn into his circle, and that was really great. I did have a request to share the slides. Can I ask the coordinator to do that for the students? Okay.
Yes, sir, we'll share the slides.
Okay, excellent. Okay, well, thank you for all of you for your kind remarks. It's really a pleasure to see you all, and I wish you good luck. Like I said at the very start, I think you're born under the right star, because I think mathematics today, or let me just say more generally, analytic thinking is it's so strong, and there's so much beautiful math and computer science and other areas that use analytic thinking. So those of you that have this ability, you have a great future ahead of you. And you're in the right country too, because I think that India, I mean, of course I've mentioned ISI, Kolkata, but there's so many wonderful universities. So I hope you all get a great university education as well. Okay, I think that's it.
Yes, sir.
All right. Sorry, I can't hear you. Yeah. Yes. Hopefully I'll be back to India soon. Oh, and let me just add about Professor Potter. I really hope that, I mean, she's at Pune, but she gives talks all over India. So and all over the world, but if you ever get a chance to hear her speak, please go and go to her lecture, because she's really she has this Erdős spirit. I like to feel like I played some role in giving it to her, but I think she had it even, I saw it even before we started doing mathematics. And plus she has deep feelings about her mathematics. She does wonderful mathematics. So I hope you do get to hear a lecture by her. Okay, shall we finish up?
Yes, sir. Thank you.
Okay, well, thank you very much. Thanks to all of you. I'll say, goodbye for now.
Yes.